Have you ever wanted to just reach into a sound and, I don't know, shape it? Like really grab the bass and boost it, or carve out an annoying hum and make a voice totally clear? Well, today, that's exactly what we're going to do. We're throwing out the dry theory and learning how to become, get this, signal architects. And it all kicks off with a super familiar question. Think about the equalizer on your phone or in your car. You see all those little sliders, right? You know that sliding one up makes the bass thump, but how? How does it really work? How does a computer program know how to find just that one frequency and crank it up or down? Well, the answer, it turns out, is digital filters. And these things are kind of the secret heroes behind, well, pretty much everything in our digital world. We're talking audio EQs, yeah, but also stuff like medical imaging. And the best part? The secret to actually designing them? It's nowhere near as scary as you probably think. So, I want you to just forget everything you think you know about wrestling with complicated abstract math equations. We're going to completely reframe this whole thing. Today, we are not doing math. No, we are drawing on a map. We're creating a visual blueprint for the exact sound we want. And this is the absolute key. See, the old way, you had to pick these abstract numbers, they're called coefficients, and you just kind of plug them in and hope for the best. It was like flying blind. But the way we're going to do it, it's totally visual. We're going to literally place points on a map to sculpt the filter's shape. It's the difference between guessing and having a GPS tell you exactly where to go. Okay, so here it is. This is our map. Technically, it's called the Z-plane, but let's just stick with design map, it's way more fun. So think of that big circle as the entire range of frequencies. The far right side, that's your super low frequencies. We're talking 0 hertz or DC. Then, as you kind of trace your finger around the circle, counterclockwise, the frequency goes up and up and up until you hit the far left side. That's the highest frequency your system can even handle. All right, so we've got this map. How do we actually use it? Well, let's grab our first tool. It's called a pole, and it's simple. If you want to boost a frequency, create a peak, that classic resonant sound that gives a filter its character, you use a pole. It's literally like dropping a pin on the map to create a mountain. And what's so cool about this is how simple the controls are. You basically have 2 knobs to turn. The first one is the angle, that theta symbol. All this does is tell you where on that frequency circle you want your mountain peak to be. So an angle near 0, that's going to be on the right side with the low frequencies. An angle near pi, that swings you all the way over to the left with the high frequencies. You're just aiming your boost. That's it. Okay, knob number 2 is the radius, which we just call R. This is your intensity knob. It controls how sharp that peak is. Now there's one really important rule. R has to be less than 1. Why? Well, that keeps the filter stable. You can't put your mountain outside the boundaries of the map, right? So this radius, it's all about controlling how wide or how pointy that mountain peak is. So what happens if we really push it? What happens when we slide that radius R and move our pole right up to the very edge of the map, as close to 1 as we can get? Boom, the peak gets incredibly sharp and narrow, super focused. This is exactly how you create one of those highly resonant filters that can just lock onto a single frequency with like laser precision. So the closer R gets to 1, the more surgical your tool becomes. It's like twisting the focus on a spotlight, going from a wide, soft glow to a tight, intense beam. Okay, that's pretty cool. So poles make peaks. We got that. But what if we want to do the opposite? What if we need to cut a frequency? Well, for that, we need our second tool, zeros. And zeros, this is where we really define the basic type of filter we're building. Is it going to let the lows pass, the highs, something in between? Zeros are the key. And this is the perfect way to think about it. If a pole is a mountain, a 0 is a bottomless pit. It creates what we call a null, basically a point where that specific frequency is just gone, 0 signal, wiped off the map. Now this table, this is basically the Rosetta Stone for our whole design map. It's the cheat sheet that translates where we place our zeros into the actual type of filter we want to build. You see those columns for A1 and A2? Those are those old school confusing numbers we talked about before. But now we don't have to guess. The map tells us exactly what they are based on where we put our nulls. Let's run through a couple of these. It's actually really simple. Okay, first up, a low-pass filter. The goal is simple, right? Let the low stuff pass, block the high stuff. So where do you think we should dig our pit? Exactly, at the highest possible frequency.
We just pop a 0 over at z equals -1 on the far left of our map, and boom, the high end is blocked.
And you can probably guess what's next. For a high-pass filter, it's the complete opposite. We want to let the highs through, so we have to block the lows. So we place our 0 at z equals 1, the lowest possible frequency. We just cut the bottom right out, and everything else gets to pass through. And a bandpass filter? Yep, you're ahead of me. We just block both ends. We put a 0 at z equals 1 to kill the lows, and another one at z equals -1 to kill the highs. And what's left? A little passband in the middle, perfectly centered around wherever we decided to put our mountain peak, our pole.
Okay, so let's recap. We have our tools, poles for peaks, zeros for nulls, we've got our map, the z-plane. It's time to put it all together. Let's build a simple, 4-step blueprint that you can use to design literally any filter you can think of.
And here it is, your 4-step plan. Step 1, you pick your sampling frequency. This just sets the scale for your map. Step 2, you choose your critical frequency. That's the spot you want to boost or cut. Step 3, you select R, your radius, to decide how sharp you want that peak to be. And finally, step 4, you just look at our little cheat sheet to place your zeros and lock in what kind of filter you're making. Seriously, that's the whole process.
Okay, let's make this real with an example. Step 1, let's say our sampling frequency, our FS, is 500 Hz. Cool. That sets our map's boundaries. Now, step 2, our critical frequency. Let's say we want to target that classic 60 Hz hum, or maybe we want to boost it. Okay, 60 Hz it is. Now on to step 3.
All right, step 3 is the radius, R. Let's pick a value of, say, 0.9. Now that's not super close to 1, so it won't be insanely sharp, but it's not close to 0 either. It's going to give us a really nice, well-defined peak, a perfect starting point for boosting that 60 Hz signal. And you know, this really gets to the core of why this whole method is so incredibly powerful, especially when you're making something like a notch filter. I love this quote from the source material. It says, by placing these nulls, you are perfectly blocking that single frequency. It's not just turning the volume down, it's a perfect surgical cut. It's how you get rid of an annoying electrical hum completely.
And at the end of the day, that is the big transformation we're talking about. When you start thinking in terms of poles and zeros on a visual map, you stop being someone who's just plugging numbers into a formula. You become an architect. You're actually thoughtfully designing the shape and structure of a signal. So there you have it. You've got the blueprint. You know how to create peaks, how to carve out nulls, how to build any kind of filter you want just by placing points on a map. So I guess there's really only one question left to ask. Now that you have this power to precisely sculpt any signal you want, what are you going to design?